We're going to take a look now at a Minitab exercise. What we're going to look at is something called power and sample size. And the objective that we have in this particular video is to understand what-if analysis. So we can understand these relationships that we see between alpha, beta, delta, or difference to detect, and sample size. And what we'll do is we'll use the one sample t-test. So let's now open up Minitab 17 and see how this what-if analysis tool actually works. Now we're going to turn to the Minitab, and what we want to do is open under Stat this very last item here called Power and Sample Size. And what we want to illustrate is how the choice that we make about setting up any selection of data can actually affect the probability that we're going to see a result. So as we come down here, I'm going to just walk down here. It's a little hard to hold it there. So I'm going to come down here, and I'm just going to choose a one sample t-test. And it doesn't really matter which of these I have. In Minitab here, this is the place where we start seeing all of these tests. These are our various hypothesis tests, which we'll talk about a little bit later in our course. But we're just going to choose one for example. So we're going to choose one sample t-test. I'm going to click on that. And I get this little window. Now I can't blow this up any larger size because Minitab doesn't allow me to click on a corner here to pull it up. So you'll have to do this along with me in your own version of Minitab to really understand what's happening. Now I'm going to do the first one. I will leave graph open and talk about graph, and then I'm going to close it because it becomes a little bit distracting. So what we see here, power and sample size, this is a sort of what-if analysis methodology. And so if we insert 3 or 4 things, Minitab will calculate the 4th. So for instance, if we want to understand sample size, then we have to be able to put in difference to detect. This is delta, and this is how good our measurement system is, what a difference we want to be able to detect using our measurement system, I should say. Power values, this is 1 minus beta. Remember, beta is the risk to the customer. And so 1 minus beta is defined as the power of the test. And then we insert standard deviation here. And if we go to options, we have some choices to make there. So one choice is significance level. This is alpha. So if I choose 0.05, which is chosen here, then the alpha becomes 95, alpha is 0.05. So the significance is 95% confidence interval. So this is 95. If I choose not equal, then this probability is distributed between the upper and lower tails of the distribution. So the probability of being in either tail is 2.5%. If I choose less than, then it says, okay, what I want to see is this is the upper tail, and I put all 5% in the upper tail of the distribution, and I ask how much is less than that amount. If I choose greater than, it puts all the 5% probability in the lower tail of the distribution, and it asks what's the probability of being greater than that. Okay, so we typically are going to use just the 5% and not equal. So this is going to be okay for us. We're not going to change this. Okay. So we've now set or fixed the alpha level, and that's pretty much common for all decisions relative to hypothesis testing. Now I want to show you something. In standard deviation, I can put in 1.0. Okay, I have to 0.0. And what that does is that then sets this distribution as standard normal distribution. Okay, if I choose, and if I say, for instance, put in here 0.62, okay, as the actual measured standard deviation, then what this is saying, oops, sorry about that. What this is saying is that I have a measured difference to detect, okay? So if I then put in here 0.62, that's the same ratio-wise as having the standard deviation with 1.0, and I'll demonstrate that in just a little bit. For power values, typically I put in a spectrum of power values. So 0.8, then space, then 0.9, then space, then 0.95, then space, then 0.99. And what that's saying is I have a beta value, or the risk to the customer, of 20%, 10%, 5%, or 99%. And when I calculate then, what this will do is it will say, for these conditions, what are the various sample sizes. Okay, so if I click OK, then I get this graph. Now what we'll see is these are high power sizes, if you will. So as I take a look at this, it says this is the power size. As power size gets lower here, I see this getting lower. So this is not a bad situation. And notice the sample size, 10, 13, 16, and 21 for the various powers. Okay. Now, I don't find this so helpful, so I'm going to close this here. And we see most of the information we get is actually in the session window. So the session window says here, for the difference to detect, sample size becomes this for these power levels. And it says this was the input, and this is the closest one that Minitab will calculate for that sample, because it's sampling in complete units, or units of 1. So we see for a 80% power of the test, or a 20% risk to the customer, sample size is 10. For 13, it's 90%. For 16, it's 95%, and 21, it's 99%. So there's only 1% risk to the customer if I have 21 samples. Now, many of you, when you do analysis, you want to have lots of data. What this demonstrates is we don't have to have a lot of data to have 95% confidence to the company, so an alpha of 5% risk of being wrong, and even a 1% risk of being wrong relative to the customer. And now, what happens, though, in various conditions? And that's what this methodology in Minitab does. It allows us to play what-if games. So what I'm going to do is I'm going to go to Edit Last Dialog Box. Okay. Now, I'm going to do two things. First of all, I'm going to turn off the graph. So I'm going to click this box, Display Power Curve, because I really don't want to do that time and time again. And then I'm going to change these two numbers. Okay. So instead of 0.62, I'm going to say it's going to be 1.0. Okay. And what I want to detect then, a difference is 1 standard deviation. Okay. And I want you to see that we get the same results. So this is just to help you understand that the results are absolutely the same. Okay. So as I take a look up here, I'm going to show so we can display both of these at once. Okay. So here we have the two power and sample size circumstances. And so as we take a look, it's 10, 13, 23, 99.1649. So the results are absolutely the same, whether we use measured data or I set it as units of standard deviation by putting that trigger in there at 1.0. Okay, so what I want to do now is let's demonstrate what happens as we change various parameters here. And how does this power and sample size situation actually hurt or help us? So let's say I want to have a difference to detect of 1/10. So instead of 1.0, it's 0.01. And is my difference to detect. And my standard deviation is 1. Now what happens to power and sample size? Notice how much it grew. Okay. So as we start taking a look, we want to find smaller and smaller differences to detect. Sample size grows very, very big. So what does that mean? Let's invert the thinking here a little bit. If I have a sample size of 19,000, okay, and this is 78,000 here for this power of 0.8. That's a 20% risk to the customer. But I want to detect a 1/10 of a difference of a standard deviation. So what that says is I have to have a very large sample size to be able to detect that type of difference. So this is not a good thing, because what we see is that means we have to have lots and lots of data. So what the implication is, when we have lots of data, very, very small differences will appear to be statistically significant. Now, the real fact is they may not be practically significant. So this is why we have the warning about the p-values and the difference between practical significance and statistical significance. Now, let's see what happens as we change some of these parameters. So let's go back and let's edit the last dialog box. So we saw this at 0.10, okay? And what happens if we say, I have a sample size, it's fixed, it's 30, okay? So many times you'll find that if you're in a real world situation, the boss says, we really can only afford to have 30, and so you calculate for your alpha value of 0.05, your difference to detect of 0.01, standard deviation of 1.0. Now, what's the risk to the customer? What is that beta value? So we can click on OK, and what we see is the beta value is, oops, difference to detect, it's 0.05. So that says there's a 5%, if you will, power. That means a 95% risk to your customer. Wait a minute, have you ever calculated that beta value before? Most of us never calculate this. This is why we have to have a caution about what we want to do. Now, can we correct that? Let's take a look. So let's edit the last dialog box one more time. And we say, okay, so what happens if we say, I don't want to detect a 10th or a 100th of a standard deviation shift. I want to just detect a 1 standard deviation shift. Now remember, in most distributions, when we are talking about something, we see 6 standard deviations in a population. So we are saying now what we want to be able to do is detect, is there a 1/6 of that shift in the range we're looking at? So if I click OK, and I say, what's the power now? So wait a minute, with the 30, the power is 0.99, so that means there's only a 1% risk to the customer. Now, if you remember when we were talking before about what happens at 30, this is the point where the normal distribution underneath this changes to the student's t distribution. And above this, the normal distribution is an adequate representation of the amount of risk that we have in a product. So as we're seeing here, this sample size of 30, it only has a 1% risk to the customer, 5% risk to the company. That's a very adequate solution for saying I've got a good sample. So one rule you might want to keep in your mind is 30 is a good distribution in terms of understanding what's happening to the customer. But let's edit this last dialog box one more time. And let's say, okay, let's just ask another question. And so we say 30 is an interesting answer. What happens if we go and I say, I want to have this 0.99 power value, oops, excuse me, Yeah, one thing you have to be, I'm glad I messed that up because I don't want you to edit this out of the video. One thing you have to be is you have to be very consistent in terms of how you put your points in. So there are 2 different ways that that Microsoft sets up your software. I'm used to using the American system, which uses a decimal point as a delimiter. In the European systems, it uses the comma. So if I have if I revert and I use the period or the decimal point instead of the comma, Minitab says you're not being consistent. So when Minitab is first installed in your system, it will choose that based on your lookup to your function. So here I'm on now a European laptop, not my own, and so you can see that that problem exists. So now let's see what happens. I want a power value of 99, 1% risk to the customer. But what I see is I can do that with a sample of just 21. I don't need those extra 9 samples. If I edit the last dialog box and I say, okay, but what if I want to have now balanced risk, which is, I'm going to call it 5% risk to the customer and 5% risk to the company. Say, oh, I can do that with just 16 samples. So as we're taking a look at this, we can say, what's the right situation we'd like to have? How many samples do we really need to take to say, in this rational subgroup, I know there is a difference or there's not a difference? So this is the value of power and sample size. Again, we can take a look at this one more time. And we haven't changed quite everything yet, but if we say we have a fixed sample size, and so let's say we have 30, and I want to see what is the difference to detect that I want to have for power value for this for a standard deviation. So the difference to detect comes up to be a 0.68. So again, now that we've done that, I think you'll agree with me that this tool will help you understand a little bit more about the types of risks we're actually accumulating in the process. And remember, what we want to do is balance alpha risk, risk to the company, and beta risk, risk to the customer. As a matter of fact, if we have to have a bias, we should have less risk to the customer than to the company. So this will then help us to understand, do we improve the measurement system, delta, the difference we need to detect, or what sort of sample size should we appropriately take to make sure that we can make a statement with good confidence?